Hi everyone, this is the Hungry Math Professor here, and today I want to do um, a fairly simple demo, but it's something that it's an example that I really enjoy. If you've taken a second semester of calculus, then you've probably seen this example. It comes from the block where you do infinite series, sum of infinite numbers, and you talk about whether it converges or diverges. I won't get into any of that detail here. I just want to stick to a very simple example, but you may have seen this before in a class, but I just think this example is so simple and so pretty. So let's look at it. And so first of all, let's just think about the following idea. So I want to take 1/2, and then I want to add it to um, 1/4, and then I want to add it to 1/8, and then I want to add it to 1/16, and then I want to add it to 1/32, 1/64th. And I want to keep doing this forever, right? So the fractions get smaller. And of course, in this case, I'm going to rewrite this in a second to notice that these are powers of in the 2 in the denominator. But what I like about this example is if you've never seen a sum of infinite numbers before, there's something very simple about it. I can basically, I think, explain this to a child or someone who has very little experience with mathematics, as long as they can appreciate the fractions, but you don't even really need to remember how to add the fractions together in any kind of way. You just have to um, be able to appreciate what these fractions are. And what I like about this example is it has a little bit of a surprising element if you've never seen this before, because I think there's some basic intuition that if you add infinitely many numbers together, you should get infinity, right? And until you see an example where you don't, this is sort of the default intuition. And so you need to see an example that shows you that this is not the case. Just to be clear, if you add one to itself infinitely many times, then yeah, you're going to get infinity. That's not going to be interesting in this sense. So you have to sum numbers that are getting smaller if you want to have some hope of getting a finite answer. So that's what's happening here, right? Now let's rewrite this a little bit differently. So we can think about this as 1/2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the fourth plus 1 over 2 to the fifth. You get the idea, but let me just finish out here what I have written. And so in mathematics, we often will introduce some notation for this. So we use this big sigma for infinite sums. We start at n equals 1 to infinity, and we're summing 1 over 2 to the n. And so what the notation says is that you start at n equals 1, which is what I would say is going on right here, and look at 1 over 2 to the n. Then you go to n equals 2, n equals 3, n equals 4, so on and so forth. I'll just finish out. And you keep stepping the n up by 1 and adding the term that you get when you do that. Okay, so this is just a nice compact notation that mathematicians use to discuss these infinite sums. Here, I don't want to get too much into that notation because I want to focus on the pretty part here. And the notation is useful when we try to get into the theory, the general theory. Okay, so I want to convince you that this sum does make sense and does converge to a finite number. And so I'm going to just do something very visual, right? So I'm going to draw a square whose side lengths are each 1. Okay, so the length of this side is 1, and the length of this side is 1. And I'm going to give each of these terms a name. So I'm going to call this A1, A2. A here is being used for area. You'll see why in a second. It's because it's going to be a part of the area of this square. And so My goal is to put all of these little pieces, A1, A2, A3, so on and so forth, into this square. And that will be a way of convincing you that um, they sum to something finite if I can stick them all inside of this square. Okay. So for A1, I want to have a rectangle of area a half. So if I just break this guy in half, then, and I just look at the bottom rectangle, then this has area half, right? Because it has a height of a half and a length of one, so that area is a half. So there you go. There's A1. And now I want to put A2 into the business here. And so I notice, again, this has side length a half. So that means this has side length a half. And so if I go a half in this direction, then I know that this square has area 1/4, 1/2 squared, right? Now you see the squaring part because the 1/2 times the 1/2 gives you 1/2 squared, or a fourth. Okay, so I have a place to put A2, a nice pretty place. Notice A2 is half of what's remaining. That's an important factor here. So now I want to put A3 into the business. And so I'm going to go halfway on this guy. And if I do that here, I get 1/4, or 1/2 squared, times, of course, this side is already a half. And so this will be 1/2 cubed. Perfect. And again, I had twice as much as what I needed to stick A3 inside of the square of side lengths one. So now I keep playing this game, and the pattern continues. So it starts to become, um, not so surprising. Here I go a quarter, and I already had this is also a quarter. And so I can put a fourth in there, and the area will be 1/16. And then if I go over here and do the same business again, now this will be 1/8, and my picture is going to get a little tight, but that's okay. And I can put A5, and then over here, I can go an eighth as well, and I can put A6, and I'm going to stop here in a second, but I can put A7, and this will now be 1/16th, and I got to stop because the picture is going to get unnecessarily messy. But the point is that every time I go to put the next square, so I go to put A8 in, now we're talking about 1/256. But the area that I have left is going to be 1/128, twice as much as what I need. And so when I go to put the next one in, always have twice as much as what I need, and I can just continue to do this forever. I'll just draw without labeling now, right? So, and the point is that I always have twice as much what I need, so there's always enough room to put the next rectangle. That you have to convince yourself, think about it a little bit, but so far you see that that's the case, and you can write down a careful argument to see that that's the case, or just observe what's going on in the geometry here. And then also, you can convince yourself that the size of what's remaining is getting arbitrarily small. And so that means that as I continue this process, the amount of the square, which is not taken up by um, rectangles A sub n, will become smaller and smaller. So as I continue to add, the part that's remaining, the part has not been taken up by a rectangle, will become arbitrarily small. And so in the limit, as we sum all these fractions, it will become identically equal to 1. So the sum of these areas, the way that we would say, this equals 1. So you can sum infinitely many numbers and get a finite answer such as 1. And now that you see it in a very geometric visual way, I think there's no way to doubt this intuition. Right now, you might have to think a little bit more carefully about this little limiting process to make sure to kind of like work out any doubts that you have. I encourage you to do that. Ask me some questions in the comments if you want, if you're disturbed by any of this. But this is well established, and this is just one example of what's called a geometric series. So there are a whole family of geometric series where you can explicitly know exactly what the sum will be. And this is a part of a whole theory called infinite series that is very pretty and useful and shows up in calculus 2 and then shows up in lots of other different places. So I hope you enjoyed this simple video. If you've never seen an infinite sum before, I hope that this surprised you and maybe you want to check out some other things on the internet about it now that you've seen an interesting example. So please like, comment, and subscribe, and I hope to see you at another video.